Hello friends, I welcome you in lecture number 1 on complex integration. From this lecture onwards, we are going to discuss about integration of complex functions. Integral of complex functions is different from the integral of real functions. When we are considering integral of real function, for example, if we are writing integral of fx over some interval a to b, then here our function is defined at every point on some interval which is a subset of the real line. But in the case of complex functions, we are not on the real line, we are considering our complex function and which is defined along some curve. Suppose this is the curve denoted by capital C from this point, say z0, to this point z1, then here our function is defined at every point on this curve and we are considering integral of this complex function along this curve C. So first we will understand how or what is the meaning of contour in the complex analysis, and we will then discuss that how we can integrate complex function along given contour. So before going for the meaning of contour, we just understand the meaning of curve C in the xy plane, which we are already familiar. For example, if I consider straight line between 2 points, suppose I have a straight line passing through origin and I am considering this part of the straight line between these 2 points. This is 1 plus I and this is z equal to 0. Then we know that this C represents a part of the curve which is the line y equal to x from z equal to 0 to z equal to 1 plus I. And here if I want to represent this curve C, then if I consider any point on this curve C, say z, then z is x plus iy, and because y and x are equal, we can write z equal to x plus I times x, and at this point value of x is 0 and at this point value of x is 1, so we can write that x lies between 0 and 1. And if we consider, suppose we take x equal to some parameter t, then because x lies between 0 and 1, we can write that t lies between 0 and 1, and here instead of writing x plus ix, we can represent this as t plus I times t, where t lies between 0 and 1. So here we have used parametric representation. Here x is t, y is t, and t lies between 0 and 1. So this is another representation for the given curve C. We can write z equal to t plus it, and in general we can write x as a function of t plus I times y as a function of t, and t lies between some real numbers, say a and b. So in general we can say that this represents a curve in the complex plane C if we can write z in this form, where this x and y are continuous functions of parameter t. So sometimes we will consider parametric representation, and sometimes we can consider this x as the parameter. So all we will understand is that we will be given some curve along which we have to integrate given complex function, and that curve C will be represented as z equal to xt plus I times yt, and this x and y are functions of parameter t, where t lies between two real numbers a and b. So this is the meaning of curve in the complex plane. A curve in the complex plane is the set of points z between two fixed points where we can represent z as xt plus I times yt, and xt and yt are continuous functions of the real parameter t. Now if we consider this representation, and if we are considering increasing values of t, that is suppose we have t between 0 and 1, then if we are considering t equal to 0, then 1 by 2, then 1, so we are considering increasing values of t, so that is called positive sense of t. Whenever we are considering values of t in increasing order, we will say that we are considering positive sense on C, or we can say that our curve C is positively oriented, or we can say that our curve C is having positive sense. So all we have to understand simply is that whatever curves we are familiar from our school level, we are familiar with parabolas, we are familiar with circles also. So all these are curves in the complex plane, and we are going to write them differently. For example, if I have this parabola and suppose it is given by y square equal to x, then if I want to represent this in the parametric form, then I will take x equal to t, then I will take y equal to t, then x will become t square. So if I want to write this in the form of curve in the complex plane, then I have x, z is x plus iy, so I can write x equal to t square plus I times y equal to t, and whatever portion we want to consider of this curve, depending on that portion our t will lie between two real numbers. So whenever required, we will convert our curve either in the parametric form, or we will keep either x variable or y variable. We will try to write down our curve either in this form x plus ix, or if required we will write in the parametric form also. This is also parametric form, but here I am not taking x equal to t, I consider x as variable. So in short, we will try to represent the equation of given curve which is containing two variables x and y. We will try to convert the representation of curve from two variables to single variable. That is the idea of these complex line integrals. So, and one more thing, suppose our curve is having no corners. Suppose we have this curve, and suppose we consider curve which is in this form. This is curve C1 and this is curve C2. So we can see that in curve C1 there is no corner, but in curve C2 there is a corner. So if there is no corner point or this type of point in our curve, then we will call that curve as smooth curve. And the curve which is having at least one corner like this, then it is not smooth curve. We are not going into the detailed definition of smooth curve, but smooth curve is that curve which has no corners inside it, and if our curve has corners, then it is not a smooth curve. For example, if I am considering this part of the circle, then it is a smooth curve. But if I am considering this type of curve, I am having triangle like this, then this is not smooth curve. But I can consider this as a union of two smooth curves. Suppose I consider this portion by C1 and this part by C2, then I can write this curve as the union of C1 and C2, where C1 is smooth curve and C2 is smooth curve, but this union is not smooth curve because I am having sharp corner at this point. So I can say that this curve, suppose this curve is denoted by C, then it is equal to union of C1 and C2, and we call this curve C as piecewise smooth curve, because we can write it as a union of two smooth curves. So if our curve is not smooth, but if we can represent it as a union of finite number of smooth curves, then we will call it as piecewise smooth curve, and this piecewise smooth curve is given name as contour. Whenever we use this word contour, then contour is that type of curve which is union of finite number of smooth curves. So contour is nothing but piecewise smooth curve, and we will remember this, that contour is piecewise smooth curve, that is, it is the union of finite number of smooth curves. So in our in complex integrals, we are going to consider some complex function which is defined along given contour, and now contour means piecewise smooth curve, and smooth curve means there is no sharp corner in that curve. So this is smooth curve, this is not smooth curve, but both of these are contours. C1 is contour because it is union of one smooth curve. C2 is also contour because it is union of this curve is also contour. We can consider it as union of C2 and C3. So this is also not smooth curve, but it is union of two smooth curves, therefore it is contour. Now sometimes we will have this type of curve, that is, if we are considering circle, approximately assume that this is a circle, then this is also smooth curve, therefore it is a contour. But we can see that if we start from this point, then if we start with this point and if we move along the circle, then we come back at this point. So we can say that this point, this curve is that type of curve in which initial and terminal points coincide with each other. So that type of curve is known as closed curve, and if it is union of finitely many smooth curves, then we will call it as closed contour. Closed contour means a piecewise smooth curve whose initial and terminal points are same. Sometimes we will have this type of contour. Suppose I am considering this contour, then this is also contour, and we can see that if we start with this point, then after completing whole curve we will end with this point. So here initial and end points are same, therefore this is closed contour. But here we can see that this contour cross itself. So if our contour is crossing itself, then we can say that it is not simple contour. Simple contour means like this. If we are considering circle, then this is simple contour because it does not cross itself. This is also simple contour. If we start with this point, then it does not cross itself, and this is simple as well as closed, therefore it is known as simple closed contour. So we will require the meaning of all these words in upcoming lectures. For example, if I consider, say, this curve, suppose I consider this type of rectangular curve, then this is a simple closed contour because it does not cross itself, therefore it is a simple contour, and because its initial and terminal points are same, it is closed contour. So this is simple closed contour or simple closed curve. And suppose I consider this curve, this starts with this point, and if we consider along this direction, then this is also closed contour, but it is not simple closed contour because it crosses itself. So the curve which does not cross itself is called simple contour, and if it is closed, then it is known as simple closed contour. So we are going to understand all these things, and we will see that how all this terminology is going to be used in the concept of complex integration. Without understanding all these terminology, you will not be able to evaluate complex integrals or contour integrals. So we again recall, we started with curve in the complex plane. So curve in the complex plane can be represented as zt equal to xt plus I times y of t, where t lies between two real numbers a and b, and these two are functions of variable t, and they are continuous functions of t. So this represents a curve or arc in the complex plane. Now if there is no sharp corner in the given curve, for example, if we consider this curve in the complex plane, then there is no sharp corner in this curve. So that type of curve is known as smooth curve. And if it has finite number of sharp corners, then it is called piecewise smooth curve. So either we have smooth curve or piecewise smooth curve. Both are known as contours. So contour is a piecewise smooth curve, but here number of sharp corners must be finite. Now suppose our curve starts with this point and it ends at this point, then it is known as closed contour or closed curve. And if our curve is closed and it crosses itself, then this is closed curve, but it is not simple closed curve. Simple curve means curve does not cross itself. If curve crosses itself, then it is not simple closed curve. So remember all these meanings, and we are going to use all these terminology in upcoming lectures to understand complex integrals or contour integrals. So I have tried my best to explain the required terminology for complex integrals, but if you have any doubts, you can ask me, and we will recall all this terminology whenever required in the upcoming lectures of complex integration. So I stop here. Thanks for watching.